In this video, we're going to go through an example, question 21 from the pure Year 1 textbook Review Exercise 1, based on the Chapter 3 topic involving simultaneous equations and inequalities. This question's got two parts. The first one asks you to solve these two equations simultaneously. So we have y plus 2x equals 5, which is a linear equation, and then 2x squared minus 3x minus y equals 16, which is a quadratic equation. When we get to the second part of the question, we'll see that it's using very, very similar things. It's still got the 2x squared, the minus 3x. Instead of a minus y, it has minus 16, but perhaps that's related to the 16 on the other side of this equation. And over here we have 5 minus 2x, which looks a lot like y add 2x equals 5. So we're going to see why they've used the word hence when we get to part B. And the fact that we have a hence or otherwise suggests that any valid method could get you the marks, but you'll probably find the most efficient approach would be to make use of the result you've already found from part A. And it might well be that before you even dive in and find the answers to part A, you can think about how they might help you with part B. In this case, and in fact with most questions, it's beneficial to think in terms of what you're expecting to get out of the question, what your solutions will look like, and how you'll know that you've got them right. So as a very quick starting point, you ask yourself what you know and what you need. Well, what you know, I've just copied down the relevant bits of the question. I need to write out those two equations in order to solve them. What I need are the solutions. What do they look like? Well, in the context of simultaneous equations, solutions will involve an x value and a y value. Solutions of the form x1, y1, for instance, two values, a value for x, a value for y. But also, there'll be potentially a second solution because we're solving a linear with a quadratic. Now, if you actually graphed these, you would see that it looks something like this. We've got a quadratic equation, we've got a straight line going through them. So we can see that we're going to have a couple of solutions. But in general, you don't necessarily know if you're going to have two solutions or possibly just one solution where the line ends up being perfectly tangent to the curve and potentially no solutions. Questions involving those will typically ask you to find a value of k for which the line is a tangent or something along those lines, or to demonstrate that they don't cross. What we're looking at here is two equations that do cross, and they cross in two different places, so I'm expecting two solutions. Now, when we solve simultaneous equations, if they're both linear, then you might use elimination or substitution or even plug them into your calculator. If one of them is more complicated than that, then we always go with substitution. And substitution means we need to rewrite one of the equations, typically the simplest one, in a form that allows us to substitute it for one of the variables into the other equation. So 2x squared minus 3x minus y will be 16, but y is equal to 5 minus 2x. So I can plug that in place of y. This will work even if you've got a y squared in here. All it means is we're taking two equations involving two unknowns and converting it into a situation where you have one equation, potentially quite a complicated looking one, but involving only one unknown. And that allows us to take that equation forward and solve it. If we simplify this a bit, taking care with those negative signs, we get this. By grouping terms, we have 2x squared minus x, and then by moving the 16 onto the left, or equivalently subtracting 16 from both sides, we'll get this quadratic equation, 2x squared minus x minus 21. Now, while I'm talking, I'm also grabbing the calculator to plug in the numbers 2, minus 1, and minus 21 into the quadratic equation solver. And it's giving me solutions. You should never spend more time than you need to on solving a quadratic, because you're never going to be given more than 1 mark for correctly solving a quadratic equation. So even if you're super quick at factorizing, it may not be quicker than just subbing the numbers into the calculator. Tip: if you want the factorized version of this, notice that a root of 7 over 2 does correspond to a factor of x minus 7 over 2, but also to the equivalent factor 2x minus 7. You see, factors, when it comes to something like a quadratic, we're thinking about the algebraic factor that matters. So you can think of any number as being a factor in the same way that if you don't care about fractions, you could argue that 7 does divide by 2. It's 7 times 3.5. And you could say the same thing here. If this quadratic has a factor of x minus 7 over 2, then it also has a factor of 2x minus 7. So if you wanted to factorize this and you cared about making sure that it was exactly the same as this expression, you could do it, but it's going to end up looking like 2x minus 7 times x plus 3. If you write it as x minus 7 over 2 times x plus 3, then it would still give you the same solutions if you're solving for equals 0, but it will be a different graph that you're representing. It will be a squashed down version of that graph. So whether or not you factorize, whether or not that's the process you've used to solve this equation, doesn't really matter. What matters is you've got the two solutions that you need. And thinking back to what we were expecting, we want a value for x and a corresponding value for y, and then potentially a second value for x and the corresponding second value for y. So we need to take both of those solutions for x, 7 over 2 and minus 3, and we need to find the corresponding solutions for y. At this point, we're going to make use of the fact that we already know that y equals 5 minus 2x. That's the simplest of the two equations we've got, so it makes sense to sub our values into that one. But also, even though you could theoretically sub them back into the quadratic equation, you would, depending on how complicated the quadratic was, you might need to solve a quadratic then and find the two different values for y and then figure out which one of them satisfies both equations. So at the end of the day, you might end up back at the linear equation anyway. So you might as well start there. 5 minus 2 lots of 7 over 2 is of course 5 minus 7, so that's minus 2. And if we make this really clear what we're doing, we could say something like x is 7 over 2 implies that y would be minus 2. It's not enough just to get two values for x and two values for y. We need to know which one corresponds to which. So the solution, or the actual coordinates of the point where they cross, is 7 over 2 minus 2. And if you do have a graph, you can check that that's consistent with your approximate sketch. 7 over 2 is over here, 3.5, minus 2 down here. My curve has been distorted a little bit. If I turn it back into more of a 1-to-1 scale, you can see that it fits a little better with what you might expect to see. 7 over 2, in other words 3.5, and minus 2. So that seems plausible. Another solution we can find by subbing in minus 3. Get y equals 5 minus 2 lots of minus 3. And because we're taking away negative 6, that's equivalent to adding 6, we get 11. If you do make a sign error along the way here, comparing with a graph, if you've managed to draw a graph, is a good way of verifying your results and spotting any errors that might have crept in. Minus 3, 11 seems to fit with the picture we've got here, so that's encouraging as well. Those are the two solutions we were asked for. If you're curious, we'll include this diagram in here for your later reference. But that wasn't the end of the question. That was the end of the first part of the question. The question requires us to not only solve the simultaneous equations, but also to find the set of values for which 2x squared minus 3x minus 16 is greater than 5 minus 2x. So for this, how are our two solutions from the previous part going to help us? Well, if you think carefully about what we were dealing with, y add 2x equals 5 is the same thing as y equals 5 minus 2x. Not only that, but if we have our quadratic, 2x squared minus 3x minus y equals 16, that one is equivalent to y equals 2x squared minus 3x minus 16. You might recognize both this expression and this expression in the question that we were looking at over here. The inequality requires us to work with those two expressions. And each of them is basically what y equals. So when we think about this graph that we were looking at before, The value of y gives you the height of each graph. The red line is the linear equation and the blue curve is the quadratic equation. And the question is really asking us to figure out when the quadratic is higher than the line. And we can see it from the graph. It's obvious from even a rough sketch. And it doesn't matter if you've not got a perfect sketch for yourself. It doesn't need to be a particularly pretty sketch. It certainly doesn't need to be exactly accurate. You know the equation of the two. So you know, for instance, that the quadratic is a positive quadratic. And you know that the line has a negative gradient. That is enough in and of itself. You wouldn't even need to be aware of exactly where the axes were on here. All you need is some vague idea of what the x coordinates are for these points. And if you know what the x coordinates are for these points, then that's enough for you to solve the inequality. So at this point, I'd encourage a sketch, even if it's just a rough sketch. And we want to notice that the inequality we're being asked to solve, 2x squared minus 3x minus 16, is greater than 5 minus 2x. This is the same as saying when is the quadratic curve higher than straight line. So here's our straight line, here's our quadratic curve. And I use the phrase when. What I really mean is for what values of x, because at different values of x, either the line is higher or the curve is higher, and we just need to figure out when that happens, for what values of x that is the case. This is why it's a hence or otherwise question. You could rearrange this and solve it directly as a quadratic inequality in its own right. If you were just given this question without being given the other one, you could solve it in your own way. So I'll show you that in a moment as the alternative approach. However, since you've already solved an equation that turns out to be basically the same equation, you've got the critical values for this inequality. You've got them already. We know that the critical values are x is minus 3 and x is 7 over 2, 3.5. Given those critical values combined with our graph, therefore, we can identify the range of values of x for which this is true. You can see from this diagram when the curve is higher than the line. It happens if x is big enough, if x is beyond 3.5, or if x is small enough, below minus 3. So x has to be either greater than 7 over 2, or x has to be less than minus 3. It's a strict inequality, a greater than, not a greater than or equal to, and it's less than, not less than or equal to, because the original question had a strict inequality, a greater than sign. Now, that on its own should be a valid solution. Depending on what the question's asked for, we can write this differently. We could write it using set notation, which means you put these funky curly brackets around, and the curly brackets represent a set. A set could include anything you like, so it could be the odd numbers that are less than 6 or something like that. But this particular set is going to be described with a slightly more abstract algebraic approach. It's the values x for which, or such that, that's what the colon represents, x such that x is greater than 7 over 2. That is the set of values that satisfy our inequality at the top end. So x could be big enough to satisfy the inequality. Alternatively, we might have an x value such that x is small enough to satisfy the inequality. It cannot be both at the same time, and insisting that it is would only end up giving us no possible values. If I ask for a number which is simultaneously above 3.5 and below minus 3, you can't give me any numbers. There are no numbers. That would be the empty set, a set of nothing at all. What we're saying here is, if you satisfy either of these, then you satisfy the overall situation. If you've got a value of x that is sufficiently small, so it's below minus 3, or alternatively sufficiently big, above 3.5, then that is satisfactory. Since we're allowed one or other of these, and it doesn't matter which, we're going to use the OR symbol, the union symbol, and that is how you can combine the two sets using set notation. So the overall solution in set notation looks something like this. X such that x is greater than 7 over 2, union x such that x is less than minus 3. It's basically either of those is fine. The set containing all the values of x that are big enough combined with the set containing all the values of x which are small enough. And that is your solution. Just briefly, the alternative version you might have used, if we take this inequality and rearrange it, you might recognize some of these numbers, because when we write this in the standard format, we end up with a quadratic equation that looks a whole lot like the one that we solved just a little bit ago. We were originally solving this problem, we had 2x squared minus x minus 21 equals 0. And now we're trying to deal with 2x squared minus x minus 21 is greater than 0. Well, if you were solving this without having done part A, you would still find critical values, and you'd find them by solving the related equation, the one with an equals, instead of a greater than symbol. And when you found your critical values, which of course are 7 over 2 and minus 3, you would then sketch yourself a rough graph. Now, this can be as rough and ready as you like, remember, so there's no particular requirement for you to do something particularly neat and pretty. It just has to make use of the fact that we know the curve we're dealing with is a positive quadratic. Look, it's got a 2 in front of the x squared. It's not a negative number. Positive quadratic, so it's a curve with a U shape that has a minimum as opposed to an N shape that has a maximum, and it crosses the x-axis at 3 over 2 and at minus 3. So roughly speaking, something like this. That's all we really need. Once you recognize that, you can start seeing what x values will make this curve bigger than 0. And it looks like we need x values that are either that are above the value 7 over 2, or equivalently below the value minus 3. So that's what your rough and ready diagram is going to look like. It doesn't need to be beautiful. It just needs to give the information that you want to show. Once you've got that diagram and you can see the values that work, then being careful with the actual sign that you use. We had a strict inequality. We're going to have a strict inequality here. We would end up with our final results, which again would look like either this basic version or the more sophisticated set notation version. So you can use either of these depending on what the question asks you for.